All right, so class will be a little short today because the College of Science has got a meeting with everybody. It's got a meeting with the provost and the president today, so at 2. So we'll won't stay too long today. We do have one section to look at, section 2.8. Okay, so far we've been talking about functions. Today we're going to look at a special type of function called an inverse function. Okay, where anytime you have one, you really have two. You have functions that are inverses of each other. Okay. So our definition and our notation here. Let's see, function f inverse. And so the way we write down the inverse function is it looks like it's to the -1 power. Okay. That's a little bit unfortunate because that can be a little confusing sometimes. You just have to remember if we're talking about functions, then when you see that -1 up there, it means inverse. It doesn't mean to the -1 power. I'm giving you an informal definition here. So we'll say two functions are inverses if the two functions undo each other. So what we're saying is if we take some input and put it into function f, and if we take that answer and put it into f inverse, we get the input back that we started with. This is an idea that we use anytime we solve equations. We think about inverse operations. So like if we have 3x equals something, then we said that means 3 times x, so we need to cancel that out. So we would divide both sides by 3. So there the operations multiplying by 3 and dividing by 3 would be inverses of each other. They cancel each other out. Okay. So we're thinking about the same idea here. We just may have more complicated functions. Okay. But same idea. So let's kind of do one of our little bubble charts here. Okay. So we might have a function f that sends 1 to 4, 2 to 5, and 3 to 6. Okay. Then the inverse function of f, we write it like that, is going to do just the opposite. It would start with 4 and send it to 1, start with 5 and send it to 2, start with 6 and send it to 3. Okay. So that would be an inverse function in that case. Okay. One thing to take note of, okay, is that the domain of f are numbers on the left, 1, 2, 3, and those are the inputs for f. But the domain for f inverse is 4, 5, 6, right? 4, 5, and 6 are the inputs for f inverse. Okay. So that's one way to think about inverse functions, okay, is that the domain of one function is the range of the other function. Okay? The range of one function is the domain of the other function. How I should have said that. Okay? So here the range of f is the domain of f inverse. Okay. So kind of in words, inverse functions switch the inputs and the outputs of the other function. Okay. All right, so a couple of ways we can illustrate that. Okay. One thing we could do is we could list some points that would be on some function. So maybe we've got the 0.1 comma 2, 0.3 comma 5. We'll just do 2. Okay. Then on the graph of f inverse, it's got to switch things. It's got to switch the inputs and outputs. So because we know the 0.1 comma 2 is on the graph of f, the 0.2 comma 1 has got to be on the graph of f inverse. And you just switch the x's and y. Okay. And the idea is that if this function sends 1 to 2, then the inverse would send 2 back to 1, and we get back to where we start with. Okay. So if we know the 0.3 comma 5 is on the graph of f, 0.5 comma 3 got to be on the graph of f inverse. Another way you could write this same thing down, and you'll see this in WebAssign a little bit, is instead of saying the 0.1 comma 2 is on the graph of f, we could say f of 1 is 2. Or instead of saying the 0.3 comma 5 is on the graph, we could say f of 3 equals 5. Right, because this is still our input and that's our output. So if that's the case, then the way we could write these others is we would say f inverse of 2 is 1, and f inverse of 5 equals 3. So that's one good way of thinking about inverse functions, is that they just switch the x's and the y's around. Okay. X's and y's are like a mirror image. Okay. Right, so inverse functions are nice because sometimes we do want to work backward, like when we're solving equations and things. Maybe we want to undo what a function did. So we need to have some way of taking the endpoint and going back to the start. So then inverse functions are helpful there. Okay. Unfortunately, not every function has an inverse. Has an inverse function. Okay. So one thing that's nice to be able to do is to be able to check and see if a function does have an inverse or not. Okay. And the way we're going to talk about doing that is we're just going to talk about looking at the graph. So if we look at the graph of a function, how can we tell if that function would have an inverse? Okay. So here's our test. Really similar to something we've already done. Is that right? Horizontal. Okay. So vertical line test. I've got it pulled up oh, here, so we can see where we did it, I think. The vertical line test says that if we have a function, and then no matter where we draw in a vertical line, it can only touch our graph at most once. So if we can draw in a vertical line somewhere that touches our graph more than once, we know that's not a function. For the horizontal line test, we're not testing to see if our graph gives us a function, we're testing to see if it has an inverse. So any horizontal line touches the graph of a function that has an inverse, and it's still the same rule, it's still at most once. And then a little bit of vocabulary here. A function that has an inverse, that property of having an inverse we give a name. Looks like a ratio, we call it 1 to 1, or you can spell it out. 1 to 1. So saying that a function is 1 to 1 is the same thing as saying it has an inverse. So a 1 to 1 function would pass the horizontal line test. If a function does not pass the horizontal line test, it is not 1 to 1, it does not have an inverse. Okay, so let's look at a few. Questions so far? Okay. Let's look at a few. Let's see. Okay. There's our parabola. We've already talked about that is a function. But does it have an inverse? Is it 1 to 1? Can we draw a horizontal line in anywhere where it touches it more than once? Yep. There's a bunch of places we could draw a horizontal line in where it would cross it more than once. So this is not 1 to 1. It does not have an inverse. The reason why that comes up that way is like, think about this as a graph of x squared. Then the point 2, 4 would be on there. So that would be the point 2, comma 4. And then the point -2, 4 would also be on there. So the problem with that is that if we start with 4, if we think about if we had an inverse function, and if we start with the y value of 4, where does it go? Does it go to -2 or does it go to 2? It can't go to both, because if it tries to go to both, it would not be a function. That's why the horizontal line test works. So anytime you have a graph where you've got both ends going up or both ends going down, okay, pretty much it's going to fail the horizontal line test. Let's see, we could have one that looks like this. that one would fail the horizontal line test. If we draw a horizontal line through here, it touches more than once. And so that function would not be 1-to-1. It would not have an inverse. Well, let's see what kind of, make sure they don't throw you any weird curveball graphs in here. Yep. Yeah, I'll give you a graph or something like that and say this function 1-to-1, or does this function have an inverse? That's either one. Yeah. If we have something like this, that one's okay, because no matter where we draw in a horizontal line, the most it would touch our graph is once. Excuse me. Okay, so this would be 1-to-1. It does have an inverse. Question on the horizontal line test? It's not too bad. All right, just the main thing now, you got to remember which one's which. The vertical line test tests to see if it's a function. The horizontal line test tests to see if it has an inverse. Yeah, but they work the same way, just one's vertical, one's horizontal. Okay. All right. If we don't have the graph, and we need, if we just have like two function definitions, inverse function property, sorry. There's another way we can check. If two functions are inverses, I'm going to say if functions f and g f and g, sorry, then two things. Okay. F composed with g of x equals x, and g composed with f of x equals x. So we talked about function composition last thing on Tuesday. So we can use that as a test to see if two functions are inverses. We do the composition both ways around, okay, in both orders. And if both times we get x after we simplify, just only x, then the two functions are inverses. Right? That would basically mean that f cancels out g and g cancels out f, and we just get the x that we started with. Okay. So, the important though, you have to get x both directions, okay, in both orders. Just having one order is not enough, okay? Because sometimes we could have one where we get x and the other one we don't. Okay? So that would not be an inverse. Okay? So let's Let's try that a little bit. Mm. So we want to know our F and G inverses. Okay. So it looks like maybe. If you think your way through it, square a number and add one, and then the other one says you take away one and take the square root. So maybe. Okay. The way we check it, just need to find f of g of x and g of f of x and see what we get. So remember, on this one function is going to go inside of the other function. Which one's going to go on the inside this time? G. Yeah, G goes on the inside, the one closest to the x. So we want f of g of x. So f of x is x squared plus 1. G of x is square root of x minus 1. So if we plug that in the place of x in our function f, we'll have the square root of x minus 1 squared plus 1. If we square a square root, what happens? It cancels out, goes away. So that leaves us with x minus 1 plus 1. The 1's cancel out, and that leaves us with x. Okay, so it's looking good so far. We did g inside of f, we got x. Okay. But that's not enough. Okay. We've got to check the other order as well. Check the other order as well. So we need to find g of f of x. So that means f goes on the inside this time. So we want g of x squared plus 1. G is square root of x minus 1. So we'll have square root of x squared plus 1 minus 1. A little low there. So in there, we really don't have to have the parentheses. I just put them in there so you can see where I was plugging in. And so there, plus 1 minus 1 goes away. We got square root of x squared. Have to be careful here. This one's a little tricky. I don't remember if we've talked about this in this class yet. What's the square root of x squared? Close. It's not just x. Not just x. This is actually absolute value of x. So, side note here, sometimes it depends on how good of an algebra teacher you had. Okay? Sometimes we just kind of pretend like square root of x squared is x. Okay? That's not always true. And usually what's going on in the background that sometimes the teacher doesn't talk about is we can pretend all of our x values are positive, and then square root of x squared would be x. Okay? But, all right, so think about this. We're checking, does square root of x squared equal x. That's what we want to know. So what if our x is negative 1? Okay. Then we would square the negative 1, get 1. That says the square root of 1 is negative 1, and that's not true. That's not true. If we put the absolute value on both sides, then yeah, the square root of 1 is 1, absolute value of negative 1 is 1, and that works. So in this case, one way it worked, we got x. The other way, we don't get just x, we get absolute value of x. Okay. So those two functions, they look like they might be inverses, but they're not. They're not. So these are not inverses. Scroll. This one's good. Sounds bad. Not inverses. Okay. And if we'd have thought about the graphs to start with, we could tell that, because what's this graph going to look like roughly? Got x squared, so it's going to be a parabola, and then the only thing that's happened to it is it's been shifted up 1 unit. So parabola fails the horizontal line test. So it can't have an inverse. Can't have an inverse. Okay. Questions on that one? If you do go through that process and you get x on both of them, then they are inverses. I won't make you sit through another one. Okay. So, last thing we want to do, that's where I think it's the last thing. Yeah, last thing we want to do is we want to talk about, if we know a function has an inverse, how can we come up with the inverse function? That's actually not always possible. Okay. It's possible that we have some function, we know it's 1-to-1, maybe the graph passes the horizontal line test, or there are other things that are a little more complicated you can do to test to see if the function is 1-to-1. We might have a function that we know is 1-to-1, but we don't have any way of solving and finding its inverse. We know it has one, but we don't have any method to find the inverse. Okay. Most of the functions that have inverses in 112, we can find. Okay, we can find the inverses. It's not always the case, but most of the functions we'll deal with, we can find. Okay. So, if we know a function has an inverse, how do we find it? Okay. So here's the process. Okay. So step number 1, and this first step you don't absolutely have to do. It just kind of makes the notation a little less confusing. But step number 1, if it's called f of x or g of x or whatever it's called, so I'm going to change f of x here, but it could be g of x, h of x, whatever the name of the function is. We're going to change the name of the function just to y. Okay. And that just simplifies the notation a little bit and makes things a little bit less confusing as we move forward. Step 2, we're going to switch all of the x's and all of the y's. Usually we only have one y. We're going to switch them. So everywhere we had an x, we're going to change it to y. Everywhere we had a y, we're going to change it to x. And then step number 3, we're going to solve for y. So we want to get it into a form that says y equals something. Okay. So then y equals the inverse. When we get that solved for y, that thing that we have will be the inverse of f. Let me see how what the answer boxes look like. Yeah. Okay. All right, you got the steps. Put them down. Okay. So let's try it. We want to find the inverse of this function. Okay. We're going by those steps. First thing I'm going to do, just to make the notation a little simpler, instead of calling it f of x, I'm going to change it to y. I'm going to say y equals 7x minus 2. Okay. What's step 2? Switch x's and y's, so instead of y equals 7x minus 2, I'm going to have x equals 7y minus 2. Remember, it'll help remember this step if you remember you're trying to find an inverse, and you can think about inverses. What they do, they switch x and y. In step 3, this is usually where most of the work comes in. We need to take our new equation we have and solve it for y. Okay, so I'll rewrite it, and then we'll go from there. So I'm going to add 2 to both sides. Okay. And then we want y by itself, so what's our last step? Yeah, divide both sides by 7. So x plus 2 over 7 will be y, and that is f inverse. So here's this is what I would put in my answer box on WebAssign. Questions on that one? Okay. Yeah, we're gonna do a few more because we kind of want to see some different flavors. Get a variety here. So same thing, we want to find the inverse. F of x equals 1 plus cube root of x. So I'm going to call that y equals 1 plus cube root of x. I'm going to switch my x's and y's. So x equals 1 plus cube root of y. And then I need to take this thing and solve it for y. Okay. So first thing, if I'm trying to get y by itself, is I can subtract 1 from both sides. So I get x minus 1 equals cube root of y. But I don't want cube root of y, I just want y. So I need to cancel out that cube root somehow. So what can I do to both sides? Cancel out a cube root. Well, it's close. And not multiply, we're going to raise it to a power. Raise it to the third power. That's right. So here we can raise both sides to the third power. That's like squaring a square root, but we're cubing a cube root. So we end up with x minus 1 cubed equals y, and that is f inverse. Here's our inverse. Question on that one? Okay. Okay. That's the general idea. The only thing that makes them harder is how hard you have to work to do this step. Some of them are a little messier than others. That one was a little bit trickier because you had to raise both sides to the third power. Let's do another one. So I won't write the directions down again, but we want to find the inverse. So this time we'll start with something that has an exponent in it. Okay. So step 1, I'm going to call it y equals 2 minus 3x to the third, or 3x cubed. Okay. Step 2, switch the x's and y's, so x equals 2 minus 3y cubed. And then step 3, we want to solve this thing for y. So we can subtract 2 from both sides first. What we need to do next? Yeah, we gotta get y by itself. So right now we got negative 3 times y cubed, so we need to get rid of the negative 3 part. So we'll go into divide by negative 3. Yeah, so x minus 2 over negative 3 equals y cubed. Okay. But we don't want y cubed, we just want y. So how can we cancel out that third power? If it was y squared, we could take what? If we wanted to cancel out y squared, we could take the square root. It take the cube root, yeah. So we can take the cube root of both sides. I didn't leave myself enough room there. It looks weird. So cube root of x minus 2 over negative 3 equals y. So that is f inverse. Okay. And that's okay. Don't worry about it. So now that maybe some of you have never heard this thing before, that square root of x squared is absolute value of x. You don't have to worry about it when we have an odd index. That's just x. The cube root of x to the third is x. Fifth root of x to the fifth is x. Seventh root of x to the seventh is x. You know, only have to worry about it with even powers. Okay. One more, just so you see one like all of them you have to deal with. We end up with a lot of third powers on these because we could go bigger, we could go to fifth powers, but when you have even powers, a lot of the time you don't have an inverse, kind of like we saw with the graph of x squared. So, let's see, so what do we have? 2 minus x to the third over 4. So the only part on this one that looks a little bit different is that the whole thing's over 4. I just want to refresh your memory on what to do there. And so, all right, y equals 2 minus x to the third over 4. Then we need to switch x and y, so x equals 2 minus y to the third over 4. Now we need to solve that for y. So how do we get started on that? Yeah, multiply both sides by 4. Because if we multiply by 4 over here, it will cancel and we'll get 4 over there. Sometimes people forget about doing that. So. Okay. So then from there, it's not that much different from what we've done. We would subtract 2 from both sides. Really, 2 ways we could go about this, since it's an odd power. What could we do next? We could divide by -1. Yeah. Okay. So there, or you could think about multiplying both sides by -1. That would be okay too. You end up with the same thing because we just get a minus sign out in front of 4x minus 2. It will probably take it with the -1 in the denominator. But this is like the more standard way of writing that. Okay. And then last step, trying to get y by itself, so cube root. Yeah. So we'll have cube root negative 4x minus 2 equals y. And that is f inverse. And like I said, it would probably take it if you have cube root of 4x minus 2 over negative 1. It'll probably take that too. So they're equivalent. So. And then the other way I was thinking, just give you another option. You could go ahead and take the cube root of both sides here. You would have cube root of this equals negative y, and then you could divide by negative 1. So just the only difference at the end would be that the minus sign is outside of the cube root, and since it's a cube root, that's the same thing. All right. Y'all ready to go? That's okay. We are done as long as you don't have questions. Okay. If you do have questions, feel free to hang around. I've still got a little time if you need help with anything.